Hi, Alan.
Yeah,
Oh,
yeah.
hi.
Okay, let's start. And we are recording. So, good evening, everyone, and welcome to our second ACM Chicago event on explaining and accelerating machine learning with finance. And our speaker this evening is Dr. Mark Bennett from NVIDIA. And yes, this talk is going to be recorded, so you will get an email afterwards for the recording. So this talk is also co-hosted together with IEEE Computer Society Chicago. So IEEE basically is like the sister section or so of ACM. It stands for Institute of Electronic and Electrical Engineers. And the Computer Society is one of the societies of IEEE in the Chicago section. So basically, we've done through last year a lot of joint events because a lot of the topics that we deal in ACM Chicago are also the same computing topics with IEEE Computer Society Chicago. So we've done lots of joint events together. So I'm the chair of this organization. The vice chair is Gina Martinez. And you can see here that this is where we advertise and our previous and our next events. So we have our web at ieeechicago.org/cs, our Facebook page, IEEE Chicago, our Twitter, LinkedIn, and we also have a Vimeo channel where you also can see our previous talks. And so there are some members this evening that are from IEEE, so thank you for them who are coming this evening. Also as well, we also have members from the Mid-America Club IT Connect. So the Mid-America Club is a private business social club. It is on the 80th floor of the Aon Center. So you may know about the Aon Center or you've been there. We've actually held previous talks. In fact, actually, before the pandemic last year, we had a talk from Databricks that was in February last year at the Mid-America Club, where we would be serving, food and drinks and have our meeting up on the 80th floor, which has a really beautiful 360-degree view of Chicago skyline. Now, this is also an IT club as well. That's held within Mid-America Club. So we've also done lots of things together with IEEE as well as ACM. So the chair is Vijay Konkamala, and I'm the vice chair. You can see the URLs, websites here. This slides will be provided after this presentation, so you will get a copy of this. So you don't need to record this down. So we also welcome Mid-America Club members tonight this evening. And of course, our main host is ACM Chicago. So I am the chair of ACM Chicago. Our vice chair is Mark Temkin, and our treasurer is Greg Newmark. And a lot of you here have gone to our previous meetings from last year. So we thank you for your support of ACM Chicago. You will see our next events at chicagoacm.org. We primarily use the meetup, so I think most of you here have known about this talk this evening from our meetup site. We also have Facebook, Twitter, LinkedIn, and we also have our YouTube channel as well, where you'll be able to find our previous events. So I'm now going to turn it over to Mark Temkin, our vice chair, to kind of give you a preview of our next event, and then he will go ahead and explain about our featured presentation for this evening. So Mark, go ahead.
Hi, everyone. As you can see, our next slide here. Next month on February 17th at 6 p.m., our speaker is Jeff Sullivan. You can see him there on the left, who 17 years ago left a career in the tech industry for what he describes as a quest to help change computer science education. Jeff is the computer science and making teacher at Lane Tech High School, whose graduates have earned more doctorates than any other U.S. public high school. Jeff, who created the Lane Tech Maker Lab, is going to share the motivations and processes used to create the Digital City of Chicago 3D map, which is a 48 square foot 3D map of the 77 community areas that make up the city of Chicago. And he will talk about the digital design and digital fabrication tools, software, printers, cutters, and mills, and how he and his colleague led a team of 150 students in two-person teams to create the 3D map. Jeff is a winner of a National Educator Award. He's designer of the Solon Flatback Face Shield and has appeared in media including WGN News, NPR, and Medium, and he's written for Make magazines. He has collaborated with partners from Argonne National Labs to the Chicago Cubs. So you can sign up now for our February 17th event with master teacher Jeff Solon on a collaborative digital fabrication project with Chicago high school students. You don't want to miss this one. In March, next slide. On our next slide. There we go. Thanks. In March 17th, our following speaker is Volker Muller, who trained as an architect and then transitioned to developing 3D modeling and design software to integrate the flow of knowledge about a design project from inception to construction. In his talk, Computational Opportunities at the Digital Physical Interface and Infrastructure, he will discuss how automation and computation are uniquely positioned to affect progress in the construction industry. Make sure to attend this talk on March 17th at 6 p.m. Complete information and sign-up information will be available on our meetup site soon. And now for tonight. Tonight's presentation, Explaining and Accelerating Machine Learning for Finance. And if we can move to the next slide, there we go. Okay. So Dr. Mark Bennett returns tonight for his fourth talk to the Chicago ACM after his initial computational finance talk in 2008, going to Monte Carlo simulation and computational finance in 2013, and financial analytics, building a laptop laboratory for data science in 2016. I first met Mark when he was asking questions from the speakers of our very first GPU computing presentation way back in 2008. I immediately asked him if he wanted to be a presenter. He said yes, and the rest is Chicago ACM history. Originally involved in aerospace in California, Mark returned to the Chicago area to work on the fastest tech applications in the area, computational finance, where he worked for trading firms, Bank of America, and now works for NVIDIA. Mark is co-author of Financial Analytics with R, published by Cambridge University Press, which is being used as the textbook for his course at the University of Iowa Department of Business Analytics this fall. So let's welcome tonight's speaker, Dr. Mark Bennett.
Well, thank you so much for that warm introduction, Mark. I really appreciate that, and Alvin as well. And can you hear me okay before I go too far?
Yes, we can hear you, Mark.
Okay, great. I'm going to share my screen and start this presentation. Okay, how are we doing there? We're all good? Okay, great.
I'm not seeing your screen
we don't
yet.
see, yeah, we don't see your screen yet, yeah.
Okay, I know what I do with Zoom. You got that extra click. Share.
Yes.
We got to
Yes,
confirm
it's
that.
showing up.
Here we go.
All
Yeah,
right.
we see your
that
desktop.
happened before. How about now? Okay.
Yes, go ahead.
Okay, great. So good evening. And it's great to be here for the fourth time. Algorithms are changing our lives at a rapid rate now. So boosting and backpropagation running on massively parallel hardware are being applied to robotics and medicine and autonomous vehicles. For finance, the changes are not quite so obvious because the artifacts of finance are not as visible. We're not talking about machines necessarily. We're talking about maybe computers in the back room. They tend to be quantitative formulas, bar charts, plots, and are realized in, well, people investing in securities, buying a new car with a loan, say, or creating the ability to retire. So let's talk about combining machine learning with financial engineering. So we have our traditional financial engineering on the left-hand side, and in the upper left, those of us that have worked in loss forecasting know the best practice approach is to look for the distribution of expected loss, unexpected loss, and stress loss. And we have to estimate those from the data. So it's a relatively simplistic probabilistic model. It doesn't necessarily change itself for the number of rows available of data. So now when we get to the middle chart, which is pricing and risk, people who have done this probabilistic modeling also have traditional models. For example, the Black-Scholes model. They might do scenario generation. Now, in the lower right, we need to combine the machine learning approach because there are so many big data advantages. The machine learning approach, as you may know, modifies itself for every single row in the data set. So that's an example of XGBoost over there. And it's operating, in this case, on just 2 inputs of the California housing data set. And so we have, the number of rooms, and we have kind of the neighborhood ranking in terms of income and so forth. And then we come up with a prediction of what the home price would be. If you go to Zillow, it's going to run a model very much like this. So the question is, how do we combine all these? It's happening more and more today in finance. So let me just take a step back and let's look at the outline for a minute. So we're going to talk about the machine learning backdrop, some generalities there. Then we're going to move to GPU computing, and we'll talk about what that's all about if you're not familiar with it. And then machine learning acceleration, followed by machine learning explainability, and finish up with 2 financial machine learning applications. One of them I have a demo recorded for. Hopefully that'll all go well, and then you get an example of how that runs in terms of real-time performance. So that's kind of our outline there. And so on to machine learning in the backdrop there. It's revolutionizing so many industries. And let's look at finance in particular. On the left-hand side, we have a traditional historical approach. For example, we have a theoretical mathematical model that is believed to be the best practice model because so many people have vetted it. It's relatively low in complexity in many cases. For example, if we were to write down the Black-Scholes formula, not the proof, but the formula, it would only occupy maybe a third of a page of paper. So not a lot of math there to explain the model. And you might have a champion and a challenger model. For example, you might have, if you have American options, you might challenge the Black-Scholes model with something like a binomial tree or Monte Carlo simulation. There could be various challenger models, and there have been. And you come up with your best one. On the right-hand side, we have the machine learning approach, where we train a classifier that's customized for each instance of data. And then we have classifiers compete for the best accuracy. So again, we have a competitive environment. It's just that the high complexity of the machine learning approach is what allows it to describe all the nuances. So machine learning, being data-driven, take advantage of these distributions of large data sets, and in many cases able to make better predictions. So let's put that on hold for a minute. And if you're familiar with machine learning, then more power to you. But you may not be all that familiar with GPUs. And I first encountered GPUs in 2008, right around the time Mark was describing about one of the ACM talks. And if you look at the application areas, it's very rich right now in terms of data analytics. For example, the upper left, we actually are looking at a financial data set. That's the Fannie Mae loan data set, where the red is showing where the defaults are occurring, and the blue is showing you the total number of loans. And we can see California, many loans in the Midwest and Texas, and kind of like you'd expect the distribution to be. Now, another area that's big is simulation, whether it's molecules, galaxies, black holes, or weather. Three-dimensional simulation is very important. GPUs are needed simply because of the compute demand there. So then we have AI with particular computer vision, robotics, also a big area for GPUs, as well as graphics. And there are graphics, for example, ray tracing now, there's a whole revolution in that technology is coming out where you simulate the rays of light all the way from the eyeball to the objects, exactly the way physics does the work. So that's a very important area. And powering all this is our latest GPU known as the NVIDIA A100. So we're going to talk more about that on the next slide. But behind all that is a software stack that includes things like Merlin, Jarvis, which allow you to handle recommender systems, as well as natural language processing and speech recognition, which are all important for AI. And then finally, in the lower right, we have the data center, which is the scaling up of hundreds of GPUs all coordinated together. And it's very challenging to get them all together and working on a problem, but it can be done, and I can show you many applications. So here's the Ampere, the A100, and the innovation here is that it's 7 nanometer technology and a total of 54 billion transistors. So that has a number of streaming multiprocessors and a total of just about 7,000 ALU cores. Okay, so they're able to coordinate in addition to the tensor cores, which work on the matrix multiplication. It's really geared for a dual use case of either high performance computing, HPC, or AI. So those are the two highlighted on the top. And then in the lower left, we have the sparsity acceleration, which is particular to Ampere because of the number of zeros in the neural net training use case. We can simply get a 2-for-1 factor, a 2x out of that. And then great innovation is that the GPUs can be sliced 7 ways. So the A100 can become a multiple instance GPU where you can have, say, users that don't have high demand, 7 of them can share 1 GPU. So that's sharing the resource very well there. And then in the lower right, we have the NVLink and all the interconnect handling the ability to do strong scaling, where we add GPUs and are able to make them nearly 100% in terms of the incremental improvement that they gain on the problem that they're solving. So that's the A100. And when we put 8 A100s together, we come up with the basic unit of computing here in the data center, which is the DGX A100. So now the GPUs themselves are here, and they, of course, are packed together and need to be cooled. And then they get put together in this rack unit, and then those racks can be put in the data center, and we're linked with NVLink. And then furthermore, our business partner, Mellanox, who invented InfiniBand, it allows all these DGX systems to talk to one another. So that's kind of the schematic, and there's a really interesting graphic that kind of dissects it if you look on YouTube for the DGX A100. But in terms of applications, so they're powering autonomous vehicles, and this is our range of the NVIDIA Drive platform, and you can see it goes all the way from a very low power, meaning 5 watt, with 10 trillion operations per second, all the way up to 800 watts and 2,000 trillion floating operations per second. And this is doing object recognition. So the training is done in a data center, but then it's the neural nets are downloaded for object recognition, and we can go, all the way up to levels 3, 4, and 5 in terms of the autonomous vehicle space. So there's a number of car manufacturers that are working with this GPU architecture. And then I was telling Barry Finkel just before the chat that, and we both are have Argonne in our background, and a very interesting project formed by, over here in Lamont, Argonne National Laboratory is working on COVID. And so they have the first DGX A100 supercomputer fighting COVID-19, and it's a 24 node cluster, and it has a total of 192 A100 GPUs. So it has a Mellanox high-speed switch fabric and a total of 120 petaflops of AI computing power. And this is being used as we speak, delivered about middle of the last year. So let's talk a little bit about the acceleration of machine learning now. Back to machine learning, we had our GPU background, and there's an ecosystem called Rapids that works very much like the Python pandas system. You import a library called cuDF instead of pandas, and now you're able to do GPU accelerated data science. So you're able to take your tabular data and slice it with SQL-like statements. You can find min and max. You can do all the functions that you need to do in Python. And you can see the ecosystem is very rich in terms of people that are using it and contributors. I have another slide that talks about contributors specifically with one of the machine learning classification systems, which is XGBoost. So in terms of the layering, we've got the Python-based data frame solution, is a series of layers that go all the way down to the hardware. So when you use rapids in the upper left-hand side in purple there, you can see that underneath you is all the CUDA available linear algebra code, graph analytics, as well as signal processing. Anything you need to use is part of that as well. So that's the NVIDIA Rapids Python-based data frame solution. And combine that with machine learning classifiers, and now you're able to do your machine learning. So let's talk a little bit about the boosting algorithm. And this is used as a reference here, the famous book, Elements of Statistical Learning, where they introduce boosting. And of course, XGBoost is a variation of the boosting algorithm. What's really unique about these types of decision tree models is they've come a long way in the fact that boosting focuses on the toughest part of the data set. So it has a series of weights that are initially it doesn't know any better. So it goes out and assigns W sub I equal to 1 over N so that they all have the same value. But then based on the error function, as it observes whether the value of the function is equal to the actual value or not, it comes up with an error function. And it recomputes the weights, and it works iteratively like that. So that's the boosting algorithm, and that's inside of our supported XGBoost package, which is supported in Rapids, which means it's GPU accelerated. So that's really handy in terms of when you're running XGBoost, you know, a dozen or more times a day, maybe dozens of times. Every time it runs, you're going to get GPU acceleration behind that. You can see the number of contributors over there. And actually, our demo has XGBoost in the loop. And let me just talk a little bit about what you can expect. This is on a little bit smaller GPU, an RTX. We have 2 Titans or 1 Titan, and we go from 18.1 seconds on the CPU. We go over on the GPU. When we have 2, we can get that down to 4 seconds. So it's a minimum of 3-fold speed up per GPU when you add it. And in my demo, I think I get something like 8 times as well. So now that's the small end of the spectrum. As we start adding GPUs and we can coordinate them, we get into kind of the big leagues. And this is really an interesting chart that was presented by our chief scientist. And I found it on our corporate repository. I thought it was very interesting. On the left-hand side, we have image classification, which was really making progress between 2012 and 2016. And then furthermore, from 2018 to 2020, up on the upper right-hand side, we have the NLP, the natural language processing classifiers. So let's look at back to 2012. We have AlexNet going to ResNet. It's a demand of about an order of magnitude. So we look at the petaflop second days, right? So petaflops per second, the total number of days we need in order to train our classifier. And so the demand goes up with ResNet. And when we go from ResNet to the very end, we actually have a factor of 30,000 in demand. So we start with BERT and 2018, and then we can see how we're riding up this curve where the demand for these more accurate NLP classifiers goes up and up every year. And in 2 years, it's gone up by many orders of magnitude, and you can see it there in the right-hand side. So GPT-3 is a classifier that has 175 billion parameters that it has to estimate during training. So it's just getting crazy out there. So let's talk about another aspect of machine learning, not only acceleration, but the big thing now is explainability. Okay, so you have a classifier that works, but can you explain the model to me so I understand the decisions it's making? So the best practice approach that we're really following lately is called Shapley. And Shapley is a mathematician who wrote a book in the 50s about game theory. And he was able to, we are able to now use the game theoretic approach to the feature attribution. So if we have F, a model F of X, where X is a vector, and we need to find out the predicted value from F, we can come up with an explanation model that's very similar that will explain through the details of the Shapley values. So if we look at the middle, we have G of Z prime, and we start with a bias term, and then we look at the attribution of the features, and we add those up and we get our answer. For example, when we do our loan example we're going to be doing soon, we're going to show you the Shapley values, which show the attribution of features. And it's different than the feature report that you typically get because it has the signs attached to them. So it tells you whether you're more likely or less likely, say, to default on a loan. So that's the very useful feature of it. And it's done with a combinatorial equation at the bottom. So each Shapley value for the feature I is the sum of the incremental contribution with and without I, using all possible combinations not containing I. So that's a formula that is intractable, but through approximation, people are able to get reasonable time and cut down on the complexity of the algorithm. And that package is already written. You simply say import shap in Python. If you don't know about it, I think it's really handy for you to experiment with it. And so let me just say shap in the upper right here is supported in Rapids and XGBoost as of now. In fact, I've run it many times and it was available since right around October. So that's GPU accelerated. It's not only available in XGBoost, but it's available through Rapids as something you can run much faster on the GPU, up to 20 times faster. So now we're over to the machine learning applications. And let's talk about the two sides of the world. And, you know, those of you that work with money, and you know that you either have debt or you have equity. So if you have money in the bank, that's equity, or maybe those would be investments for you. And on the left-hand side, you have debt. You might have a mortgage or you have a car loan. And so we're going to look at both sides of the house there. So on the debt side, we have mortgage delinquency prediction. So that's a binary classification problem, much like credit risk scoring, where we are taking the Fannie Mae data set, again, that's public, that are real loans, and we're going to attempt to classify them. We're going to train our classifier, and then we're going to ask how well it does in predicting cases that it's never seen before. And on a similar note, we're going to do that with equity in the asset management space. And instead of the credit risk, we're going to look at the Kalmar ratio, which is the ratio of the return over the period divided by the maximum drawdown. And so that will be a 20-year, and it'll be regression. It'll be a numeric value rather than simply a 1-0 value. So just comparing and contrasting our two use cases here. So let's look a little bit at the Fannie Mae mortgage data set, and you can see now there are about 50 so fields, not a super wide data set, but everything you'd need to know about a loan. For example, the seller names are there, although I blanked some of those out. The interest rate is important, and you can see we're in 2007, 2012. So these are 6.6. These are higher interest rates than we have now. We can look at the unpaid principal, and all these features contribute to whether or not the loan would become 90 days past due. When it becomes 90 days past due, there's a whole decision tree of events and what can happen. Either you know, the lender has to call the obligor and work out a way to either refinance or some other action. It may lead to default. It may lead even to foreclosure. So there are different outcomes. But the bottom line is that 90 days, the loan is in trouble. So you can see that we have the loan to value, which is the amount of debt that the person has, and then the number of borrowers is real easy to see there because it's either 2 or 1. Typically, it's a household number. If they're co-signer, then you have 2. Otherwise, it's an individual with 1. And so these are all predictable. And when we run our example, and we followed a Bank of England paper that led us into this idea. And they did it with UK loans. We've done it with the American loans, which the run here is with 11 million actual loans. And we get a really good speed up factor there. We go from you know, 600 seconds, which is 10 minutes, just to read in all the CSV files for this huge data set. That's 30 times faster when we move it to the GPU, when we run it on the older model NVIDIA 100, and the A100 is even faster from what I've run. We can also do XGBoost, the classification, which is the middle of the page right here. And we can do that, the fit function, 8 times faster, which saves us a lot of time, of course, if we're running our data science experiments. And then you can see the last step there, the SHAP tree explainer, which is the one we've been talking about. That's over there at 22 times faster in the lower right. So just to show that graphically, we can see that the mortgage analytics acceleration, here's the reading in the data, and then the key would be the training, the third one, and then the last one. And of course, the longer line is when we just have a CPU, and then when we have a GPU, we can get our job done so much faster. So that's all about accelerating the entire workflow for machine learning. So now we can talk about the Shapley values and what they look like. So this is the distribution of all the Shapley values across the 11 million row data set. And we have delinquency equal 1 being the positive case, meaning we're interested in delinquencies because we're putting ourselves on the side of the lender. And we can see from the first row, the distribution is such that the higher the originating interest rate, the more likely we are to default. And that makes sense because that's a higher payment. It's harder to afford. Yet on the next row, credit score, the higher the credit score, the less likely because we're simply more credit worthy. So that makes sense from a Shapley perspective as well. And then as we go to loan to value, we want the loan to value ratio to be low because we don't want a lot of debt. If we have a lot of debt, that puts us in the red zone. We're more likely to default. And you can see how these work. And these can also be found on an individual loan basis as well, but I thought I would show it in the aggregate. So Shapley explainability done 22 times faster on the GPU. So that was one of our applications. That was the debt side. And just have a little bit more here about the equity side of things. So let's talk about an algorithm that is asset management case. And this is published in the paper link below, and you can get a copy of the slides if you're interested. 18 securities. These are international securities, right? And you can see they range from oil, gold, silver, S&P, Nikkei, Euro stocks, Canadian dollar bonds, so fixed income instruments. So a pretty good sampling in terms of diversification. And then we want to compare different investment algorithms. The first one in the upper right is called naive risk parity, or we simply abbreviate RP, where we weight the stocks, these 18 stocks, based on the inverse of their volatility, meaning the more volatile, the less we trust them in the portfolio. So that's naive risk parity, simple algorithm. The next algorithm is equal risk contribution. So we measure the risk contribution. We look at the covariance matrix, which is sigma, and we make sure that each security has an equal risk contribution. Now, the third one is the one we're interested in, which is a relatively new machine learning based one. It's a tree clustering algorithm that uses a quasi-diagonalization, which manipulates the covariance matrix in a recursive algorithm, and it's documented in the book Advances in Financial Machine Learning. So in a way, we're doing a best practice again. We're looking at all three of these, and we're looking at the actual market and how they did from 2001 right up until the coronavirus downturn. And you can see that appearing right here in March of 2020. We all remember that. But along the way, there are other places such as 2008, 2009, where the drawdown is important to witness. And the good thing here for HRP is that it has a low drawdown during the credit crisis. So if we look at 2008 and 2009, it simply doesn't do what the other two algorithms do, which is, lose over 10%. And of course, a drawdown situation, if you start your strategy near a drawdown, then of course you lose confidence in the algorithm. So all told, if we look at the very end of it, the HRP even doesn't draw down all that much during the coronavirus. And that's all due to the complexity of the algorithm. So, so here's how we use the machine learning part of this. So I'm going to look at the various metrics, and we're going to combine these as features because we simply have price vectors. But in the financial world, we want to create statistics on these as features. So the volatility, the return, the maximum drawdown. And the key performance metrics are over here, which are the Sharpe ratio, which is the ratio between returns and volatility, which is annualized, and the Kalmar ratio. And specifically, the Kalmar ratio is the big one we're going to use, which is the ratio of the annualized return to the maximum drawdown rather than just the volatility. And we can see that HRP wins over here for the MDD. It's simply as a 9.6% versus this 13% for the others, right? And the Kalmar ratio, it also wins because it has a higher return per unit of maximum drawdown, right? Because it's at 0.6 versus 0.439 and so on for risk parity. Now, that's an interesting observation, but the problem in financial machine learning is we only have one path through the actual markets. And so we need to make our tests robust. We may go to as many as 100,000 scenarios that we simulate, and we use a statistical process known as bootstrapping, particularly block bootstrapping, where we take, as you can see here in this diagram, we take the slices of these three securities returns, and one security is particularly more volatile than the other, and you can see the returns moving around right here, and then we copy those down with replacement. So the first one goes to the first one directly, the second one goes to the fourth one, the third one goes two places, so we see this repeat of the volatile second security. And so that's known as a block bootstrap. And that's something we need to do very quickly. Otherwise, it may take us, over a day to run our simulation. And of course, we want to tweak it, and we want to get that day down to minutes or seconds. So when we do 100,000 scenarios, we certainly want to do those on a GPU. Now, to look at, say, 10 bootstraps prices for the stock Apple over a 3-year period, this is what it looks like on the right-hand side. So we have the actual Apple in the thick green line here. That's what Apple actually did over that period, and that's what we start with. But we can bootstrap all these other scenarios, and we can look at, what the Kalmar ratio was during those as well, and that makes our experiment robust. So we look at the difference between the Kalmar ratio with HRP versus ERC, because we're expecting HRP to win, and in every scenario it does come out ahead, but the question is by how much. And the other question is, what are the properties of the securities that explain why the HRP would work better? And so we're back to Shapley values. So this is a Shapley plot that has come out of that study, and it shows all the created features, financial features that can be done specifically on the commodities or on the equity part of the portfolio of those 18 stocks. And so it's a little bit of a twist. We're not focusing on predictive accuracy. What we're doing instead is running the XGBoost classifier so that we can then run it again for the Shapley values, and then go and examine the Shapley values and see which features are the most prominent ones. So that's kind of an interesting twist. And not only did we move from, debt to investments, but we were using machine learning for something else this time. So what I'd like to do now is show the 2-minute video that shows the running, and I kind of explain, and this was recorded earlier today. And what I'm going to do is bring up the recorded video in the other window, and we're going to expand it. Hopefully you're still able to see my second screen. It says I'm sharing my screen. And how does that look, Mark Temkin? Is that okay?
That looks good.
Okay, thank you. Okay, so when we start this, which is right here, this will take about 2 minutes, but it's running on a V100 GPU, and it's running so much faster. This would take a half an hour to run this. This is a Python notebook, and it's getting started right now. So we do all our imports, and we go and get 11.2 million loans. In fact, the loan part of it is already done, because that was done in probably less than a second. But then and there they are. They're called acquisition. Now the performance itself, that's running right now, and you can see these are very big files, gigabytes in size. And so the performance data associated with the loans is very big, but we only care really about whether the delinquency was made. And so that's a particular column. So we wind up bringing a lot of that in and then joining it and throwing it away. And that's all happening right now. And so we're able to then do some displays and make sure that, you know, we have our checkpoints. We're getting to the point where we're running XGBoost. So XGBoost is running right now. If you remember the chart from before, it runs 8 times faster on the GPU, but it still takes about 30 seconds to run on the GPU. And typically we get high accuracy, but our precision and recall is difficult to hit near 100% because this is a class imbalance type of run. So here we have XGBoost. We can see by the star right here that XGBoost is running. And like I say, that's probably the one step that takes the longest. That'll take about 30 seconds. And you can see whether we're on the GPU or not on the GPU, we have slightly different parameters. And the fact that it's put something out now means XGBoost is operated on all 11 million rows and it's done. And then we've gone through about a 91% area under the ROC curve. It's 0.91. And then we see our feature importance. And then the last thing we do is the Shapley run. And the Shapley run, if you remember, is about 12 or 13 seconds. So when that is done, that will be down here. We'll be able to see, it's actually, yeah, it actually finished. The Shapley run was 13 seconds. So that's the pipeline running, and you can see I always say it runs faster than I can talk. I can only talk about 150 words a minute, and I'm not a very fast talker. So that's our presentation, and I hope you have enjoyed it. And if you have any questions, I'll look to both Greg and Mark for those. So thank you for your attention.
Yes, we have questions.
Oh, great.
Here's the first one is from Mux. Can you walk us through how the ideal ways for running CUDA Rapids? In other words, do we need an NVIDIA cloud service, or can we run it on our own machines, MacBooks, or by our own computer with NVIDIA GPUs?
Well, you have a couple options. If you have a cloud service provider, and many of them, they're certainly our customers, and they offer that. So you can get to a GPU via the cloud, or you do need it on the machine you're running. Now, in fact, it will look for CUDA, the import and everything will look for CUDA hardware. I know that because I have a laptop. I have a gaming laptop, for example, that has a 1060 on it. And I did a lot of this development on that. And so, yeah, you do need the hardware. But, you know, you're getting to the point where you buy a gaming laptop, you've already got it on there. It's just part of the deal. It came with it, in my case. The other one I have is a Jetson, which is an embedded computer that has an ARM processor. And that's a really cool device. There are various, I think, 3 types of Jetsons. If you want to get started for $99, you can buy an NVIDIA Jetson embedded computer that runs Linux, and it'll come in the mail. And there you go, GPU computing for under $100.
Hi, Mark. I think you've sort of answered this next question from Tom. But it says, are the GPUs used in machine learning the same GPUs used in personal computers, or are they customized for machine learning? I guess you've said that a standard GPU can be used for this, but then are there also customizations for like those data center ones?
Right. So the A100 was specifically designed, and that's, you know, the last year, specifically designed for data center level machine learning with this extra thing about the tensor cores. But any GPU that I mentioned earlier, for example, my Jetson will do object recognition much faster than not having a GPU. If I'm, you know, sending it around the room, it'll see our wedding picture, and it'll say, you know, person or people, and it'll recognize a lamp, and it'll do all that cool stuff. And it is using the GPUs. So the answer is all the above, I think, is the best way. Of course, if you get a higher end machine, you're going to get more bang for the buck, but you certainly can get an order of magnitude speed up just with a small GPU. So you can get started. That's the way I did. Like I say, $99 will get you a Jetson Nano. I have a Jetson. It's the mid-level. I think it was. I think it's right around $300, and that's an embedded computer. So that's like a Raspberry Pi. The other one is a gaming laptop where it has the GPU already there, and the heatsink takes care of the fact that they can make it very thin because they sink the heat of the CPU and the GPU, the same way through the same fan. Hopefully that answered that.
Okay, here's a question from Yugis. Have you any data on reinforcement learning applications?
We have many people in the company are reinforcement learning experienced. I am not, but all you have to do is Google. I bet if you Googled and mentioned GPUs, especially on say archive, you'll probably get dozens of people. It'll even come down to if you're talking about finance, it'll be reinforcement learning for finance or for the Go game, or it'll be reinforcement learning for any, it's game theoretic type of thing, right? So there'll be various GPU applications for reinforcement learning. And certainly it's one of the areas that has been GPU accelerated.
Okay, here's another question from Mitchell. Could you explain a little further how Shapley values are different from feature importance?
Yeah, okay. Feature importance, if you think about it, first of all, it doesn't have a sign on it. So the feature importance, the algorithm is based on the decision tree. It's, we don't always have to walk through the code, but it's the Shapley side of things, take away the feature. So let me explain more about Shapley. I actually wanted to say this in my talk. Let's say you have, and I'll use a simulation of a football game, and you take away, let's say you downgrade the quarterback. My favorite one is Aaron Rodgers. Let's say, and you put in the backup quarterback. You still have to have a quarterback. You run the game simulation again. You look at the marginal contribution of Aaron Rodgers versus that other quarterback. I don't know who their backup is now. I know I can name some names from the past. And then it's generally going to be positive. Otherwise, Aaron wouldn't be the starter. And that is that's how Shapley works. So you essentially take away the feature and you find out what the feature contributed to the outcome and the accuracy. That is not what feature importance is, though. And like I said, we'd have to probably walk through a little bit like we walked through the boosting algorithm to go beyond that. But I remember Googling this exact question, and the answer wasn't all in one place, but I think you can do it if you want to investigate a little further. And you look at, but I guarantee they are different.
Okay, next question is from Yunpa. Is there an advanced time series method in machine learning that identifies factors relevant to changes in stock prices?
Yeah, okay. Changes in stock prices. Many colleagues have done this. I've done it. I've worked with folks on this. It's very hard to predict log returns because they oscillate so much. However, again, the book Advances in Financial Machine Learning talks about fractional differencing, and they use a particular value of that function where they essentially take out that oscillation. I'll give you an example of the oscillation. When you listen to the news at night, you hear, oh, the market's up 200 points. Oh my God. Well, you look at the percentage, it might only be 1%, so it's no cause to be, angry or upset. And then the next night it's down, 300 points. The next night it's up 400 points. The next night. And there is that daily oscillation, that occurs there. Getting the direction on that is very hard to do. So what we find ourselves doing is that we look for either long-term or we look for other applications, outside of investments. If you notice, my investment application was not trying to predict the next stock price because, I had a professor tell me when I took machine learning class, he said, the signal to noise ratio in the stock market just isn't there. In other words, if you think about it, where machine learning has done so well has been in object recognition. Well, those objects look the same all over the world. If you're talking about cats, or you're talking about trains, or you're talking about airplanes, whatever, they look the same. If they look really different, then the object recognizer doesn't recognize them. So we have the challenge in financial machine learning. Those that want to predict the stock market have a relatively non-stationary random process. So, of course, people that are really good at this may be very secretive about this as well, meaning they're not going to publish their algorithm if they're making so much money. But it's very difficult, and I've tried many times. So I hope that answers that.
Okay, another question from the audience is, I was unfamiliar with Shapley coming into this. What are the limitations or common misuses of this process?
Okay, the misuses are going to be hard, and let me tell you why. It's so new that, for example, I work with 2 or 3 colleagues at NVIDIA, and then there's Scott Lundberg at University of Washington and Microsoft, and there are talks about it, but I don't think it's been used long enough for people to say how it's being misused. So I can't really answer that first one. But can you repeat the whole thing again, Mark, so I can try for the second part?
Sure, let me just, I was unfamiliar with Shapley coming into this.
Mm-hmm.
What are the limitations or common misuses of this process?
Okay, so the limitation which you may consider that overcome, and I do, is that it is NP complete and intractable. Because if you look at the formula there, we're looking at something like 2 to the number of features. Well, if you have 100 features, that's 2 to the 100th power. Now we're talking about the run, taking as long as all the, galaxies in the universe. So the approximation has to be done. That's the challenge, but that has been done by the people who wrote the SHAP package. We have a contributor and 2 of his colleagues who have then gone further and made the SHAP algorithm GPU accelerated. So like you saw, we went from 3 minutes, it was a 22-fold increase. So it was 12 seconds, versus say 360 seconds for that. And so it's quite a speed up. In terms of limitations, most people feel that it's right now the best explanation. And I recommend you looking at Tree Explainer, Deep Explainer, and Kernel Explainer. And these are all, they're all under the SHAP package that Scott Lundberg and his colleagues have put together.
Okay, we have a question from Martin O'Shield.
Mm-hmm.
We've recently been granted permission to access the Chicago Mercantile Exchange's Globex development test environment, where we can test automated trading systems. Would this Python framework you are presenting tonight be good enough for use for automated trading on the commodity exchanges of Chicago?
Yeah, it certainly would. I mean, customers of NVIDIA number in the thousands, and a lot of people are doing than what you're suggesting. Now, Globex, I think, is a type of exchange. So the answer is yes.
Okay, here's a question where someone really wants to know the secrets. From Harsha, can you share with us NVIDIA GPU architecture if possible?
Oh, a lot of it is very well documented. We're an open source company, so I'll give an example. The Shapley algorithm that was GPU accelerated, there's a 7-page paper written by Rory Mitchell, and that was published at a conference, and it's sitting on archive. You can find out probably as much as you want to know about the internal architecture simply by Googling. So the keyword would be NVIDIA, and if you have a particular chip, say the V100 has been out there so long, it's well documented. In fact, one of our financial customers wrote an in-depth analysis, outside of what we think, where they benchmarked it. They call it micro benchmarking. So there's a whole, there's many ways to find out more about the hardware. And in fact, there are several books. One of my colleagues wrote a book, and there is a professor at University of Illinois who wrote a famous book back in 2008. So you can find out all about CUDA. You can find out even to the level of the instruction set. If you want to go to that level, it's called PTX. So it's all open.
And this is referring to an earlier question where The question was about advanced time series method and machine learning changes in stock prices, and you referred to there was a book that you referred to. There was a reference to a book mentioning fractional differences.
Let me put it this way: if you're already somebody who works in finance, you might want to read that book by Marcos Lopez de Prado, and that's called Advances in Financial Machine Learning. It's a little out of my range right now, but if you want to get started in analytics and finance, I would recommend our book, Dirk Hugen and I. And you can see this is the English version of it, and we also we have it published in Korea as well, and have designs on other translations. But this is on Amazon, and it gives you an idea. Now this is using R and not yet using GPUs because it was written in 2016. But how to gauge returns? Teaches you about returns, portfolio optimization, some basic machine learning using R. So it gets you started in the field. So I would recommend it if you want to be in financial analytics. That's what I would do. But the Marcus de Prado book is more advanced. That's something that you're an industry practitioner where you've done work and you probably work in the field already. I hope that's clear.
And there's a comment here before I go into the next question that a person mentions that de Prado has a new book that is even better. So here's a question from Mitchell. Is there a reason that you use XGBoost versus a RNN architecture? Does it have mostly to do with the explainability of the model?
Oh, that's a really good question. We tend to, whenever possible, go with deep learning. But with tabular data sets, XGBoost can do quite well. And the architecture of XGBoost in terms of the number of trees that it creates and all that is all done for you. Now, as you know, if you used a neural network, you would need to select one of the 35 types. And of course, there's probably 5 that you're going to consider right away. I think you mentioned RNNs, but there's LSTMs, there's CNNs, and there's variational autoencoders and GANs and things like that. So you got to sort through that, and then you build an architecture. And then some people would call those the hyperparameters that you come up with would be your layering. And of course, it's a way to customize. So I think XGBoost is something good to start with. And I agree with you that you can oftentimes do better with deep learning. Let me explain. An area where deep learning is going to win out is object recognition. And computer vision, deep learning is number one. In natural language, you're going to beat, your neural networks are going to beat any machine learning approach. So that's NLP, and then speech recognition. You're also going to want, and those are all classified. We call that deep learning. And yeah, I didn't you didn't have the benefit of me showing you a deep learning application here, but we work with deep learning in finance all the time as well at NVIDIA. So there's no reason to think that you can't. Feel free to experiment that way as well.
And for our final question,
yeah,
how did you port your own programming skills from R to Python?
It's funny because I learned Python before R, and I was asked to learn Python in a 3-day class at work in 2013. Then I went and learned R, and I found, well, it's funny. I guess I relearned R because the thing that struck me about R was the ability, when we were doing financial simulations, to simulate a Cholesky matrix with just the characters CHOL. I thought, well, that's pretty sophisticated if you can get a Cholesky matrix, which is a pseudo square root matrix with 4 letters. So, R was written by statisticians. It's not as much of a production programming language, whereas, Python has taken on the challenge of the statistical packages of R and moved all those over. So, it's more production ready and it's object oriented. So, that's very interesting, kind of competition there. Python's coming on strong, and the way I describe that is when TensorFlow decided, right, by Google, the neural net package, when TensorFlow decided to use Python bindings, I think that was kind of, the time when Python really took over. And of course, I think they're in the lead right now. But it's all good. In fact, Some days I'm using both R and Python in the same day, but generally it's Python. I hope that helps. Thanks for all the questions. Great stuff.
Okay, take away.
Okay, great. Thank you. Thank you very much, Mark, for the wonderful talk, and thank you all for the questions. I'm going to put a poll up there, so we want to know. I'll launch the poll, so you can go ahead and answer the questions. We want to know in terms about how you learned about this meeting and give us some feedback from the meeting. And then I'm going to share my last screen, so Mark can go ahead. Mark with a C can go ahead and talk about our next talks again. So let me share my screen again. All right. Go ahead.
Okay. Well, I'm glad that I can use my NVIDIA gaming card for more than gaming now. That's what I've learned. So this is just a reminder that here's our upcoming events in February and March, which we hope you'll return to see. If you've been with our presentations, you know that we're varied every month, but we always try to get to get more interesting presentations for your direct interest, enjoyment, etc. And what you don't see also in April is we're going to have an NLP speaker, and you'll know more about that next month. So, Alvin?
Yep. Oh, did we lose Mark?
Okay, so we're always looking for new speakers, and that could be you. And as you've seen tonight, Mark was someone that I met, just heard him talking to a person, and I just said, this person, you know, he really knows what he's talking about and he can speak. And I'll just say, hey, do you want to be a presenter? Jeff Solon next month. I met him when I was trying to build up our audience for an event that was a long time ago. And he was such a inspirational and unique person that I got him to not only provide his students, he was at Northside College Prep, but also to become a speaker as well. And by the way, he originated the Chicago chapter of the Computer Science Teachers Association, which many of you might know about. So we're always looking for speakers. We look in the audience to find interesting people that we think could be speakers. And but if you want to step up, let us know. And there's where you can reach us, vice chair at chicagoacm.org and chair at chicagoacm.org. Thanks for coming. I hope you all enjoyed the program.
Yeah, so thank you very much, like the echo Mark said. So thank you all for coming this evening. And then you will get an email for those who have attended or registered to the copy of the slides, as well as the link to the video recording, as well as for our next talks as well, that you can be able to go ahead and register. And also, if any of you require a professional development hour certificate or so, I know for a lot of IEEE members, they want to have that. That will also be provided, so you can just download it and you can just put your name on there, so you can get credit for that. Okay, well, anyway, thank you very much for coming, and stay healthy, stay safe, and we'll see you at a future event. So have a good evening.
Thank you, Mark. It was a great presentation.
Thank you, everyone.
Thanks, Mark.
Thank you.
All right.
Bye.